Hello, everyone. My name is Steve, and I just wanted to come to you and bring you something that really fascinates me, and that's mechanical puzzles. However, this isn't your typical mechanical puzzle. Puzzle. There's all kinds of different mechanical puzzles out there. You can do squares. You can move around bricks, puzzle pieces, figure out how to mesh gears together and get a certain result. For me, I like my mechanical puzzles to be a bit more practical. In this case, one of the ones that really intrigues me are the puzzles involving pumping water. Because to me, the pumping the water is a very practical thing. And figuring out how to do this and do it in an entirely mechanical way is really, really intriguing. Well, this puzzle that I'm about to show you was first shown to me a number of years back on Facebook. And the puzzle comes with a certain number of stipulations, and I'll show you what those are here. This is the limitations of the puzzle. So in other words, you can't just go in there all willy-nilly and hey, let's throw a electric pump on there, plug it into the power, into the house power, and off we go. We're done. It's not like that. This one you have certain criteria which is meant to force you to follow a certain path and solve the problem, which requires you to think your way through this one. It's not slap a band-aid on it, you're done. So, anyways, the 5 rules of this puzzle were as follows. The only source of pumping energy allowed is the windmill. In other words, you can't have an electric pump, you can't have human power, you can't have any human intervention. Once this thing is turned on, it has to run and do everything itself and do it mechanically. The maximum height the water can be raised by the windmill is 10 feet. I'll explain that in a second. You'll see what I mean by that. That was also meant to keep you from cheating and just do a 125-foot lift pipe and windmill on steroids, and hey, you just solved the puzzle. So, anyways, the water that you pump must achieve a 2.5 gallon per minute sustained flow rate. That means that since this is going to supply a house, when I turn on the faucet in the house, I need to be able to get enough flow to do 2.5 gallons of throughput per minute. It doesn't mean indefinitely, but you should be able to turn it on and do that for like 5, 10, 15 minutes or at least that long. So in other words, just normal operating conditions within a house. Number 4, the entire system must be mechanical, which I explained earlier. You can't have any human intervention, no electric, none of that other stuff. It has to be entirely mechanical. And number 5, the minimum water pressure the system produces must be at least 40 psi. So anyways, that's the stipulations of the puzzle. So now I'll go ahead and show you how I solved this, and I'll explain it to you in detail, why I did it and my thinking behind it. Anyhow, the puzzle itself only stipulates that the only thing that is required is the windmill. And like I said, I have really horrible artwork, so again, forgive me for this. But the puzzle stipulated that the only thing that stipulated that was required was the windmill. For me, in my design, I added a water tower because to me that was the most practical way to get to achieve the flow rate and the minimum 40 psi. The 40 psi pressure, minimum 40 psi pressure, and the 2.5 gallon per minute flow rate. Sorry. Anyways, the tower, you can assume that's at least 100 feet at the base, maybe 125 if you want to go a little higher than that. But here's the thing that you have to remember: from here to here, if that's 100 feet, it's going to be 40 psi because you have 0.4 psi per foot of fall. You have 4 psi per 10 feet of fall. So for 100 feet of fall, which is what this is going to be, you're going to have 40 psi. This to here, if it's another 10 feet, now you're going to have another 4 psi, so you'll have 44 psi. So as long as the tower is full and you're not draining down into the dry pipe, you're going to maintain your minimum of 40 psi. If you want it higher, you make the tower higher. So, anyways. This right here is the lift pipe from the well. Now, with this lift pipe, you got 2 things with this. One, it's sealed at the top. You still got the drive pipe from the from the windmill doing its thing. So you're going to have that coming in here, but there's ways to shield that so that you don't get any contamination down in the well. Anyways, you have the outer casing when this comes up like this, and then you have the inner flow pipe, drive pipe, whichever way you want to call it. Basically, the rod goes down into the inner pipe and down to the pump itself, which then pushes the water up through that inner pipe. And the outer pipe, if the well pump for any particular or if the windmill pump for any particular reason decides to go crazy, it just overflows the top and goes back down into the well. So you're not like got to blow up your well or cause any problems or have any leakage and stuff. It just, the excess overflows and goes away and go right back down into the well, so you're not wasting anything. These two little blue boxes here are not Smurf houses. Those are accumulator tanks, and I'll explain why those are important in just a second here. This down here is your ram pump. This here is the drain pipe for the ram pump, because one of the things the ram pump does is it generates wastewater. Well, that wastewater has to go somewhere, or you're going to drown your ram pump and you're going to have water running all over the place. So that has a drain at the bottom which drains into the outer casing and goes back down into the well. So any excess water that's not used by the ram pump, the wastewater, drains away into the well and it's recycled. These are your flow pipes. The first one is when the water gets to the top, it flows over, comes over to the first accumulator tank and fills it up. This tank is roughly about 2 feet tall, which is about what you're going to want. You're going to want that much backlog of water to ensure that your ram pump has plenty of water to feed on. Otherwise it's going to stall and then you got to go restart it, which I have a way to auto restart that, and I'll show that to you in a second. Anyways, water comes into here, comes out the bottom at 8 feet, comes down to here and enters at 1 foot. Now, the reason I mentioned that is, and I'll leave this to you to study, is that if once you go and study ram pumps, you'll understand where I'm coming from on this. A ram pump has a ratio generally of about 1 foot of fall to every 7 feet, or 7 feet of lift for every 1 foot of fall. The only thing with the 7 feet of lift is once you get up 7 feet, water flow goes down to almost nothing. So, in my design, I actually reduced that down to 5 feet, allowing the extra 2 feet to produce a generous amount of throughput, or at least a respectable amount. So anyways, water comes down here, fills ram pump, it does a tuk 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 thing, and starts pushing water up to the second accumulator tank. That tank is the top of that tank is 40 feet up. Yeah, it's 40 feet up from here. By doing it on a 1:5 ratio, since you've got 7 here, you're going to have 49 maximum. I cut it down so that it's only like 40 feet of climb, so you got 9 feet of extra potential climb that now is turned into throughput, which is beneficial because this feeds a second ram pump. Now you seeing how I'm getting around this? So the windmill pump feeds the accumulator tank, which feeds the first ram pump, which feeds the second accumulator tank, which feeds the second ram pump. Now the cool part about this is this ram pump, because of where it's located at, and this is the reason it's up here and not down at the bottom with this one, is because this one, to save water, drains into this pipe and back into this accumulator tank. So any of the water that gets pumped up to here and gets wasted by the waste valve comes into here, goes down, and goes back up. So you're not wasting as much water as you could if both of them were at the ground level and they both had to drain into here, which means you get this one stays full most of the time, and this one will drain down and fill up, drain down, fill up. But anyways, this one then, it does its little tick 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 thing, and it pipes the water it then takes the water it generates and pumps it and shoves it over into the main drop pipe for the water tower. And the nice thing about this is, this would come down to a T right here. And if there's no water flowing, the water goes up into the tank and fills the tank. Slowly, but it fills the tank. Then, if it's drawing, if the tower is drawing down, that water will just join the other water and go into the house. So the yeah, okay, sorry. Anyways, then sorry, lost my train of thought. Give me a second here. This happens to me a bit. Anywho, that's what it was. Okay. Anyways, one of the things I was mentioning earlier about was that every so often, because this pipe here is only going to be 3/4 inch, just like this one's only going to be 3/4 inch. Like this could be, this one here across to this accumulator tank could be a 2-inch pipe. This one's only going to be 3/4 because that's all the ram pump is going to be able to produce as far as flow rate or production is about 3/4 of an inch. This one would down to the ram pump would be 2 inches. This would be 3/4. So you can imagine how easy it would be to drain down this tank and drain down the tank and run it out. Anyways, the simple solution to make this completely self-sustaining, and that goes for both ram pumps, because if, say, the wind dies and you get no more water going into here, this one's going to stall down here. And eventually this one will stall, and if, let's say, the bottom one stalls first, but the top one doesn't, this will fill up and overflow. This is where things get interesting. I don't know how many of you ever heard of this, but have you ever heard of those little tipping tubes that they have in the Orient? This is what I'm thinking of right here. Basically, they fill up with water here, and the way they're balanced, as that water gets to the top, this tips down. It drains out all the water, and then it goes clunk, goes right back. Well, my little idea is to use something similar to this. And like on this tank here, if the tank gets up to the overflow point, there's another pipe that comes down here into the box. And by the way, this box and this box are completely sealed. This is a completely sealed system, so that you're not going to get bugs and rodents and other things in there that might contaminate your water, because none of this is filtered. This is straight out of the well, so you have to seal this entire system to make sure nothing gets into it. But anyways, up here and up here, you're going to have an additional pipe that's going to come down into there, into this little nodding donkey thing. And what it's going to do is going to have like a little spire or spike at the end here that lines up with the waste valve. When that upper tank gets too full, this tips down. Well, when it tips down, it hits that waste valve and pushes it open. Because if the system stalls, that waste valve is going to lock shut. This will push down on it and will force that waste valve open. Then and of course when it does that, it empties out all the water, so it pops back up. And of course, once you've pushed that waste valve open, that ram pump will go click, 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 click. And if it misfires on the first time, okay, it'll keep doing it until the ram pump finally takes off. Once it finally takes off and it's no longer overflowing into that unit, then the ram pump is restarted and off it goes again until the next time it needs that. You put that on both of those, and the system automatically restarts the moment the water system is completely full. Also, as a little aside here, if you live in warm climates, this is fine. You can have these straight pipes hanging out there, and just in the air, you can have windmill over here, ram pump over here. You can have however many feet of distance you want between them, whatever's ideal for your situation. Or if you're like me, who's in Michigan, where it gets cold in the winter, what you do is you take your windmill and you cover it, you sheet it, and you insulate it. You put some kind of covering on it. It could be sheet metal, it could be wood, whatever works to insulate it, and then you run extra insulation on the inside, like Pink Panther or something, just to make it completely insulated. Then you take like this in a smaller form and you put it up here inside the tower where it's going to stay warm, and you run the pipe from that down and over to the house. And these two then hang in. These two hang inside of here. Now, doing that creates a bit of a problem, because it's the distance here and not just the fall that makes the ram pump work. Because if these are like vertical or heavily vertical, like in this example, the ram pump won't work. It has to have a certain angle for the downflow coming from the source for it to work. Sorry about that, yawning over here. So basically, if you're running it here, you can't have it vertical because the ram pump won't work. Because it literally, the downforce of the water is it's just kind of go, and it'll never go anywhere. So my solution to that was to take like a rubber hose, like a 2-inch rubber hose, and loop it around the inside of the insulated windmill tower up to the base of the accumulator tank. Same thing with this one. This one, it comes in here and then it loops upward until you get to the top of here. And, well, not top of here, bottom of here, sorry. And that's how you get the length you need and still be able to contain it within the tower where it can stay warm. And then, like in the winter, if it gets like really stupid cold outside, you can take a Coleman lantern, you can take a tray of candles, like the scented candles or the jar candles. You take them out there, fire those up. Those would be more than enough to keep this warm during the winter, so that it doesn't freeze up. But again, that's taking it into special circumstances into account when designing this. But anywho, that's the puzzle, and this was my solution to that puzzle. And I wanted to share it with you, and I'm curious to see what each of you think of it, and if you have any thoughts, different ways you might have done it, ways to improve the design. I'm game for that. I mean, one of the designs, if you don't want to do the water tower, might be to make it all self-contained, like I previously mentioned, and have a big accumulator tank out here, like the pressure tanks you have for your house. Maybe have a 100-gallon accumulator tank. You could like park that inside if you had to, again for the wintering part of it. Park that inside, and you achieve the same thing as this with that tank. You just don't have quite the volume of the tower, but you still get the same result. And if you take a 100-gallon accumulator tank and drain that thing, you're using way too much water. But anyways, that's my presentation, and thank you for listening, and I look forward to showing you the next one. Thanks.